So we are in week 2 now. This is the first lecture of the second week. In the last lecture, we came up to the point where we were discussing transformations. So we first discussed 2D rotations, continued to combine it with translation, and worked out the homogeneous transformation matrix to represent rigid body motions together properly. And then the same we extended to 3D rotation and translation. However, this is one point. Arbitrary rotations can be represented through compositions. What kind of compositions and what rotations they would represent, how the expressions for the rotation matrix, the corresponding rotation matrices, that we need to discuss a little in detail, right? So that with the help of them, rigid body motions together, we can represent nicely. So in the transformation matrix, this part can have a large number of different possible representations primarily because none of the representations has all the advantages and everything becomes simple and hunky-dory. So all the representations have their issues. The simple thing in that is that 3D rotations are not so easily representable by simply a scalar, an angle, like 2D rotations. So typically they are three numbers related in very different ways, and which three numbers you choose, that gives you some advantages of representation and it brings in some disadvantages. So those representations which are used commonly and compete against each other, that we need to see. So one of the earliest 3D rotation representations is with the help of Euler angles. And the simple reason is that they were used in physics, which is the mother of all these physical sciences and engineering. And that is ZYZ, Euler angles. Okay. So Euler angles originally were ZYZ. Now sometimes they are referred to as ZYZ Euler angles in order to differentiate them from another representation which were to begin with not Euler angles, but something similar to that. We'll come to that. Now ZYZ Euler angles is first a rotation about the z-axis through some angle gamma, and then a rotation about the y-axis through some other angle beta, and finally again a rotation about the z-axis through an angle alpha. Now this z rotation and this z rotation do not add up because in between this has come. Okay. And now the order I said, first this, then this, then this. That is so if the rotations as referred to as about z-axis, y-axis, etc., they are referred to the fixed axis. In the case of rotating axis, the same rotation will be affected through this rotation first, then this, and then finally this gamma rotation about the z axis. Another competing representation is roll pitch yaw angles. This came from the field of navigation, where there is a ship, and if you take the forward direction, then any rotation about that is rolling. Say this is the ship, so this movement, this rotation is rolling. So left, right, left, right. That is the this should be x actually. It should be x. So no, x is this. X is this. This should be x. Okay, gamma should be x. So this is roll. This is a z, and then about the axis going from right to left or left to right, if you rotate the ship, then the front of the ship goes down or back of the ship goes down. Okay, so that is pitch. So when you pitch, you put it down like this. And finally, this is the x-axis, which is actually vertical. So what about the vertical axis? When you rotate, basically that is steering. Another word for steering is yaw. Okay, so that is why it is called roll pitch yaw angles. This is useful in navigation and also for flights, okay, for aircrafts. And with time, considering its similarity with Euler angles, this is sometimes called ZYX Euler angles, and this should be ZYX. This is writing mistake. Okay. Here also, this order of the rotations is corresponding to the rotating axis, and yaw first, then pitch, then roll. This order is the order with respect to the fixed axis. There is a third representation also, in which three rotations successively are not considered, but an arbitrary axis is considered. Not x, not y, not z. Just some unit vector is taken, k, like this, and an angle. That makes sense. So, unit vector, you ensure to have the expressions appropriate for an orthogonal matrix. And related to this, there is also another representation called Euler parameter representation, in which there are four parameters. In fact, here also there are four parameters: x, ky, kz, and theta, with a relationship among kx, ky, kz. These four are actually very closely related to these four, and these four also have one relationship among them. We will see the different representations and their advantages and disadvantages. And for each of the representation, you need direct representation and inverse solution. That means if you know these parameters, these coordinates, the three Euler angles, the three roll pitch yaw angles, or this axis and this angle, or these four parameter values, then how to find out the rotation matrix. That is a direct representation. On the other hand, if you are given the rotation matrix, then from there to get the values of these, that is the inverse solution. So you write these three component matrices and simply multiply. Just multiply any two and then multiply with third in the proper order. Okay. So matrix multiplication is associative, but order is important. Now, in the inverse solution, if you are given this matrix in terms of 9 numbers, and you verify that they are orthogonal matrix, they constitute an orthogonal matrix that is given R. To find out the values of alpha, beta, gamma, you can do it in several ways because actually you have 9 equations in only 3 unknowns. Many of the equations are dependent. So you can follow this kind of order. Now, several orders you could find. This order has been prescribed for accuracy and to reduce the floating point errors. Now you see R31. So this is R31 and R32 is this. If you square and add these two, then sin square beta will be common and cos square gamma plus sin square gamma will be 1. So it will be sin square beta. Square root of that is sin beta plus or minus. Okay. Divided by cos beta, that is R33, that is tan beta. That is why you take the tan inverse of this, and that is the angle beta. And then after knowing angle beta, from these two, you can find out angle alpha. That also is through tan inverse. Tan inverse gives you better precision rather than simply from cosine or sine. And apart from that, tan inverse gives you the angle in proper full circle because you can take attend2. Attend2 is a function most programming languages offer, which takes 2 arguments. Okay, the numerator and the denominator, and so on. So after knowing that, then you can find out gamma. So this order has been gamma you determine from these two. Basically, after knowing beta, from the third row you determine gamma, from the third column you determine alpha. Okay. These 4 are actually not used at all, the leading 4. So you should use attend2 function for using this tan inverse thing appropriately. Okay. So this is Euler angle, and this will have typically 2 possible solutions. For every rotation matrix, it will have 2 possible solutions, and they will be difficult when this beta itself turns out to be 0 or pi. Because if beta itself is 0 and pi, then you see here, if beta is 0 or pi, then these two merge together and you cannot find alpha and gamma separately. All that you will find will be alpha plus gamma. Okay. So that is the singularity of this particular representation. So you saw direct solution, you saw inverse solution. Now come to the second one, roll picture. Yeah, this is X. Yeah, steering is X. So there again, if you write the 3 matrices and multiply, you will get this. Okay, that is quite straightforward. And here also, similarly, an appropriate order has been advised to get the solution with good accuracy. And that typically uses this first column and the third column. Okay, that you will see. Here the first column is used extensively. Here the R21 and R11. So that is again these two. And in the third, these two will be used. R32, R33. So this is the inverse solution. So far, so good. However, roll picture actually has an inherent advantage because this refers to three different coordinate axes, So a special advantage is that the vector gamma, beta, alpha can be used for notational simplicity, because this is the angle about the x-axis, this is the angle about y-axis, this is the angle about z-axis. However, as a vector, in the vector algebra sense, it has no sense, because this vector does not represent the rotation. Rotation is a tensor, and only a matrix can represent it properly. Okay. And the three angles actually represent it indirectly. So, though it is meaningless for rotation representation, upon differentiation of this, the derivative that you get, gamma dot, beta dot, alpha dot, that indeed will represent angular velocity correctly. Because even though rotation itself is a tensor, cannot be treated as a vector quantity, and its composition is not commutative, you see, small rotation can be considered as vector, and therefore rotational velocities can be treated as vectors, and indeed you know that angular velocity is a vector. Okay. So upon differentiation, this gamma dot, beta dot, alpha dot, that indeed gives you the components of the angular velocity vector. So that is an advantage of Rolle-Picot angles, and therefore in comparison to Rolle-Picot angles, the Euler angles still stands as a good competitor, primarily because it had the early start from physics. And even today, physics textbooks amply use Euler angles. Now, so far as degeneracy is concerned, Rolle-Picot angles will have a degeneracy at beta equal to pi by 2. So, because at pi by 2, you see, this will become 0, and this will become infinite. So that is the problem. So both the representations have one degeneracy. For inverse solution, yeah. The third representation is axis angle representation. In that, we do that exercise. We align the frame of reference first so as to make the z-axis coincident with the axis of rotation k, and then give a rotation about z, and then using its inverse transpose on this side, we restore the frame of reference. Either you think in this manner, or simply you say that you represent the transformation corresponding to a rotation of theta about the z-axis in the basis for which the third axis is aligned. Third axis means z-axis is aligned to the k-axis, given axis of rotation. That is why the third column is this. Okay. Now again, if you write these three and then multiply them together, you get this. However, you will notice that in this, the elements of the first two columns are missing, because they have been eliminated using the orthogonality property of this. So there are a few steps in that. So normally some outline, some guideline of those steps we give on the blackboard, but since this time there is no blackboard, so I'll show you the derivation for that. Yes. So this NOA, this also has a little history. Several authors in the early time of robotics used to consider the three unit vectors in the orientation matrix for the robotic hand, the wrist, as NOA, normal orientation approach. That is, these are the two fingers of the hand. The direction along which the robotic hand approaches the tool, that is approach vector. This unit vector is approach. The direction from one finger to another, that is the orientation. That is the orientation of the hand. And then the other vector, which is perpendicular to both of these two also are perpendicular. So the third vector, that is the normal. That is normal to both of these, the plane of these. Okay. So that is how these vectors got NOA names, normal orientation approach. Now, R align is this matrix with these normal orientation and approach unit vectors, with the approach unit vector being K. And these two unit vectors can be any two suitable unit vectors in the plane perpendicular to this K vector. Anyway, they will get eliminated on the way. Now, see how they are eliminated. So, this is an auxiliary frame of reference with its z-axis in the direction of the axis of rotation P. So now write these three components and we will multiply. And I will show you one column to give you the direction to make the elimination steps. So multiply this middle matrix and the right matrix first. And I am producing only the first column. Nx cos theta minus Ox sin theta, that is here. And the second entry will be Nx sin theta plus Ox cos theta, that is here. The third element will be just Kx, right? Similarly, you can fill up the other columns. Now multiply these two. Second column here will produce second, and third column here will produce third upon multiplication by this. Expressions will be similar. Similar means what? This 1 expression will be similar not to 1 2, but 2 2 and 3 3, and so on. Okay. So diagonal entries will look in similar expressions. Diagonal entries will have another kind of similarity among them. Okay. So now the first term will be Nx into this plus Ox into this. So collect the cos theta terms. Nx into Nx and Ox into Ox. So that is this. Collect the sin theta terms. Okay, and plus kx square also in the line. Okay, so this is so kx square is separately sitting. Okay, and collect the sin theta terms also. Nx into minus Ox and Ox into plus Nx. So these two cancel out. So there is not there. And the third kx square that comes here. Then produce a second. So second row and this first column. Ny in now collect the cos theta terms. Next Ny cos theta and Ox Oy cos theta. That is here. Then collect the sin theta terms. Minus Ox Ny and plus Nx Oy. Minus Ox Ny plus Nx Oy. Sin theta. And the third gives you kx ky. Similarly, the third row and this will give you this. Okay. Now, milk the orthogonality property of this matrix completely to get rid of these Nx Ox terms. Okay? N and O terms. Since it is orthogonal, so this is a unit vector. Each row and each column will be unit. So Nx square plus Ox square plus Kx square is 1. So this Nx square plus Ox square is written as 1 minus Kx square. So we will retain K, we will get rid of N and O. because K is defined, known, N and O are arbitrary. Among them, they can vary infinitely. Okay. So whatever N, O you take in that plane, so as to make this orthogonal, make these three unit vectors form a right-handed triad, that is acceptable. So we try to get rid of these NO elements which have some level of arbitrariness. So in place of this, we will get 1 minus kx square. And then from orthogonality, we also know that this vector and this vector, these two are orthogonal. That means nx ny plus ox oy plus kx ky is 0. So here you have nx ny plus ox ay. So ox oy, so write it as minus kx ky. Minus kx ky c theta cos theta. Then you have here nx oy minus ox ny. Look at the locations. Nx oy minus ox ny. From orthogonality, you know that the third column is the cross product of the first two columns, and nx oy minus ox ny is this kz. So in place of this, you write kz. X ky comes as it is. Similarly, nz nx plus oz ox. Nz nx plus oz ox. That will be minus kz kx. So that is minus kx kz cos theta. And this nx oz minus ox nz. That will be this minus ky. Okay. So write minus ky in that place. And the last kx kz you will keep as it is. Similarly, you will get other columns. Now just a little organization. You have got the expressions in the sense that all the n and o elements are gone. Now the way we write that in the official version of the expression, in that this kx square and this kx square is taken together, and so you get 1 minus cos theta plus 1 cos theta left separately. And from here also kx ky you take two terms together, 1 minus cos theta, and the third term you leave as it is. Similarly here, kx kz into 1 minus cos theta minus ky sin theta. And then by symmetry, you fill the rest of the columns. I mean, you should actually develop the second and third column also all through these steps and verify that these do appear in proper places. For brevity, the way we have written c theta and s theta, or cos theta and sin theta, we also use another notation, that is 1 minus cos theta is called verse theta. We don't know how the original grandmasters started calling that as verse theta. And in further brevity, written as v theta. Considering all these things together, we get the expression like this. And the mnemonic is that in the first column, put kx, second column, put ky, third column, put kz. Then do the same thing for first row, second row, third row. That is why in the 1 1 element you get kx square. In the 1 2 element you get kx ky, and so on. Which all 9 of them you give a verse theta. Okay. And then to the diagonal terms, you add cosine theta. To the off diagonal terms, you add here, subtract here. Add here, subtract here. Add here, subtract here. So 1 minus, and what to subtract and add? The component of sine theta. Sine theta times one component of k. Which component? This is the second column, first row, put the third component here. Same thing here. Here it is minus, here it is plus. If this is minus, its off diagonal twin will be plus. And if this is minus, then its row colleague will be plus. And that is how it is. So with that mnemonic, you can fill it very quickly. And through the process that I showed, you can develop it. Now the inverse solution. Inverse solution is a little non-trivial. So given the matrix in terms of 9 numbers, if those 9 numbers indeed constitute an orthogonal matrix and therefore represent a valid 3D rotation, then you get the axis and the angle. You see, if you add these three, then with verse theta, you will get kx square plus ky square plus kz square, which is 1. And verse theta is 1 minus cos theta. And the 3 cos thetas that you get, so 1 minus cos theta plus 3 cos theta. So that is what? Plus 1 minus cos theta plus 1 minus cos theta plus 3 cos theta. That makes it 1 plus 2 cos theta. So subtract 1, that is 2 cos theta, divide by 2, that is cos theta, take inverse plus, you get theta. The moment you get the angle, then you see the pairwise of diagonal terms. If you subtract this from this, then this guy will go off. This subtracted from here will give you twice kz sin theta. Theta you already know. Divided by 2 sin theta and you get kz. R21 minus R12 divided by 2 sin theta. Similarly, the other two. That will give you ky and kx. So like this, you get the inverse solution. This representation has a very direct, straightforward connection with the fourth notation, Euler parameters. You see, this sin theta, if you break down as twice sin theta by 2 cos theta by 2, then you get a 4 here, sin theta by 2 and cos theta by 2. Leave the cos theta by 2 here, take the sin theta by 2 above. Then sin theta by 2 times kx, ky, kz, whatever you get, call them epsilon 1, epsilon 2, epsilon 3. Okay? So these will be epsilon 1, epsilon 2, epsilon 3. 3 components of sin theta 2. And remaining part, cos theta 2, that you call epsilon 4. Now this is a relationship between Euler parameters and k and theta. So k theta also had 4 parameters, kx, ky, kz and theta, and there was a relationship among these three, kx square plus ky square plus kz square. Now you have 4 parameters, epsilon 1, epsilon 2, epsilon 3, epsilon 4, same 4, okay, a little different and organized from these in this manner, and the relationship is straightforward. Epsilon 1 square plus epsilon 2 square plus epsilon 3 square plus epsilon 4 square will be 1, because epsilon 4 square is cos square theta by 2, and these three together will be x square sin square theta by 2, y square sin square theta by 2, kz square sin square theta by 2. Together, x square plus ky square plus kz square will be 1. So the sum of the squares of these three will be simply sin square theta by 2. The fourth square alone is cos square theta by 2. The sum is 1. So that is a single relationship among the 4 parameters. So since 3 parameters are independent, so there must be one constraint among the 4 parameters. Now, in terms of these half angle sines and cosines, the expressions, the same expressions, when you put in terms of half angles and therefore you can replace in terms of epsilon 1, epsilon 2, epsilon 3, epsilon 4, you will find that you get nice, beautiful, simple quadratic expressions for all the terms. And this is the advantage of the Euler parameters. You get rid of sines and cosines from your formulation. You express everything in terms of polynomials. And that has advantage in theoretical analysis, where polynomials will give you a computational advantage rather than transcendental functions. So these are the different rotation representations. Any of them consistently you can use, and then what we discussed in these rigid body motions, all that will be complete representation for rigid body motion, and with the help of these spatial representations of rigid body motions, we can do our robot kinematics in a sensible manner. As we do that, just make note of one interesting feature. A rotation matrix, a set of 9 numbers organized in this manner, actually plays two parallel roles, one dynamic, one static. This matrix you can multiply with a vector to determine where this point, the position vector of which is this vector, will go through this rotation. And that means this matrix represents an actual rotation of a rigid body with respect to a frame. Now, after this rotation has taken place, the rotated orientation also is represented by the same matrix. So the matrix can represent an actual rotation, and it can also represent the static orientation, just in whatever orientation, whatever attitude a body is. The same matrix can represent an orientation of one body with respect to another. If the two frames, every body, you attach a frame of reference. Okay. If the frames of reference of both the bodies were initially coincident, then one of them, the fixed ground frame, remains in its orientation and the other one rotates. Then whatever rotation matrix represents this rotation of this rigid body, the same matrix will now represent the orientation of the rotated body, orientation of its frame. That means the unit vector, unit x vector, unit y vector, and unit z vectors will be sitting in the first, second, and third column of this particular matrix. So the same matrix, which represents a particular rotation, also gives you the transformation to get the resulting orientation of the rotated body. So if you say that body B has this matrix as its orientation relative to body A, that means if body B had started from the A's orientation and undergone the rotation represented by that matrix, then it would come to its present orientation. So a rotation matrix has dual role to play. It can represent an actual rotation, or it can represent an orientation. And a particular orientation and a particular rotation is related by the fact that that rotation from starting from an identity orientation brings the body to this current orientation represented by the same matrix. Similar dual role is played by the 4x4 transformation matrix involving position and orientation. it can represent an actual rigid body motion, which is a dynamic event of a body with respect to a frame. It can also represent the existing position and orientation of a rigid body with respect to another rigid body. Okay. So with every rigid body you attach a frame of reference. Now the rigid body can rotate and translate. From the original configuration, it has come to another configuration. So the change from identity to something is given by that same matrix, which gives that something rigid body motion. So if this matrix represents the position and orientation of a rigid body with respect to a base frame, that means this same matrix will represent the motion, the rigid body motion, which would be required to bring this body from this position and orientation, the frame, the fixed frame's position and orientation, to its own current frame position and orientation. So this is the understanding that you must develop by developing the numerical values of some of the positions and orientations of the bodies through actual rigid body motion, and then what we discuss later will become quite straightforward. So armed with these tools, in the next lecture we will actually go into the study of the robotic kinematics, position kinematics to begin with. So at this point we stop this lecture, which completes our discussion on the spatial representation of rigid body motion. It will be throughout used in the course.